হ্যালো হ্যালো, তোমার মাইক। হ্যালো হ্যালো, তুমি অডিওটা শুনতে পাচ্ছ না? ওটা বন্ধ করো। হ্যালো, তোমার অডিওটা স্পিকারটা চলে আছে।
এই স্পিকারটা এই হ্যালো বড় স্যার।
আচ্ছা আচ্ছা, কিছু করার দরকার আছে কি? তুমি প্রেজেন্টেশন করছো? সবাই দেখতে পাচ্ছে তুমি ঠিক করছো।
হ্যালো 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 হ্যালো
হ্যালো হ্যালো। আচ্ছা আমাকে আপনি আমাকে অর্গানাইজার করে দিন। আমি এতটা শুরু করবো তো আমার তো শুরু করছি।
This conference will now be recorded.
না আসছে না তো, অডিওটা আসছে না। অডিওটা মিক্সারে ঢুকছে, যেখান থেকে অডিওটা বেরোচ্ছে যেটা সেটা কোথায় যাচ্ছে? এখান থেকে অডিও ঢুকছে, ঠিক আছে? হ্যাঁ ছবিটা আছে, ছবিটা আছে, তারা দিচ্ছে। এটা এই তোমার ইয়েটা করো তো, ও প্ল্যাকেটটা করা আছে না, ছবিটা আছে।
শেয়ার করে দিয়েছি।
হ্যাঁ ঠিক আছে, ছবি আসছে দেখো। পেনড্রাইভটা দিন।
হ্যালো হ্যালো হ্যালো।
ছবি আছে, অডিওটা আসছে।
হুম। হ্যালো হ্যালো হ্যালো। হ্যাঁ ঠিক আছে, হ্যালো হ্যালো যাচ্ছে তো, কিন্তু গো টু মিটিং থেকে ইনপুট আউটপুটটা হচ্ছে না, ইউটিউবে বেরিয়ে গেছে দেখতে পাচ্ছি। ব্ল্যাক ম্যাজিক থেকে আউটপুট বেরিয়ে গেছে তোমার। ঠিক আছে, কিন্তু হ্যাঁ ঠিক আছে, ব্ল্যাক ম্যাজিক দিয়ে বেরিয়ে যাচ্ছে। অডিওটা আমার এই কম্পিউটারে যেখানে গোটু মিটিংটা চলছে সেখানে ইনপুট আউটপুটে অডিওটা প্রবলেম হচ্ছে, বুঝতে পারছো? যে কম্পিউটারে গোটু মিটিংটা চলছে সেখানে ইনপুট আউটপুটে প্রবলেমটা হচ্ছে। এ রাখো দেখছি। হ্যালো হ্যালো।
হ্যালো
হ্যালো।
Hello? Am I audible? Am I audible?
It is audible. It is audible.
মাইকটা বন্ধ ওইগুলো সবারই মাইক বন্ধ।
Good afternoon, all of you. I welcome Dr. P. Rangababu, Assistant Professor, NIT Meghalaya, for delivering his expert talk in workshop on advanced microcontroller programming and interfacing on virtual mode from 13 March to 14 March. First of all, I request Dr. Sandeep Chanda sir, HOD Electrical Engineering Department, Goni Khan Chaudhary Institute of Engineering and Technology, Malda, to welcome Dr. P. Rangababu. Sir, please. Okay. Please wait for 2 minutes, all of you. Our director, sir, may join this workshop.
Hello.
So I am handing over the mic to our HOD sir. Sir, please welcome.
Thank you, Amarjit. What I can see, students and faculty members are still joining, but we want as much knowledge as possible from our speaker today, P. Rangababu from NIT Meghalaya. So we will not change the schedule. We shall have to start the program. At the outset, I would like to welcome our guest speaker, Shri P. Rangababu, Dr. P. Rangababu from NIT Meghalaya. I would like to welcome also the faculty members of GKCIT, and also I would like to welcome the students. I would like to thank our Honorable Director Sir for permitting us to conduct this workshop. Actually, Dr. Amarjit has already conducted one workshop, 1 week workshop on artificial intelligence, and the purpose of the workshop was to get accustomed with the algorithms, methodologies that can be implemented in the AI environment. Now, how to practically implement them? It is possible only with the help of microcontrollers, and we know that in all the smart devices, smart equipments, and in all the applications of AI, microcontroller is required. And that is why in our degree courses, in master degree I had to study microcontroller a bit. but students now have to study microcontroller from their BTech level and even in diploma level also. And the importance is such. So with this note, I again welcome our guest, and we know that this program is also important for the faculty members, because this knowledge is new to us. Certainly this knowledge of advanced microcontrollers, especially like Arduino or PIC, these are new to us. And it is especially important for the faculty members, because faculty members have much more knowledge, much more depth in knowledge, so they can understand where to use this technology. With this knowledge and experience of the faculty members and enthusiasm of the students, we know that this small electronic board called microcontroller can do wonders. So with this note, I again welcome all the participants and our guest, and I would like to request our guest to start his presentation. Sir.
Yeah.
Thank you,
sir.
Thank you
for your motivational introduction. Now I request Dr. P. Rangababu sir to start your presentation. So before starting presentation, I want to start with some formal introduction of sir. Sir has joined, before joining to NIT Meghalaya, sir has joined NIT Goa in 2013. After that, in 2014, he has joined as an assistant professor at NIT Meghalaya. Sir Rangababu has 34 essay publications and 38 international conferences. He has completed 8 funded projects, 3 as principal investigator and 5 as co-principal investigator. He has conducted 8 faculty development programs and established 3 labs. He has supervised 2 PhD students along with 30 MTech dissertations. So without any delay, now I am handing over the mic to Rangababu sir. Sir, now the dais is yours. Thank you.
Yeah, thank you, sir, for a brief about me. And today I'm going to deliver the talk on the advanced microcontroller and programming and interfacing. So this is a basic. Just I prepared the slides. Is it audible?
Yes, sir.
Hello. Is it audible?
Yes, sir. Totally audible.
Yeah. So so advanced microcontroller programming and interfacing. In this, my outline of my presentation is about microcontrollers and why we need microcontrollers, what are the various kinds of architectures are there, and what about the 8051 microcontrollers and data transfer mechanisms, because that is the building block to use some of the peripherals in conjunction with like to transfer the data from IO devices to the processor, vice versa. And after that, I will show you some example related to the Arduino programming and also some examples, and follows with the some kind of demonstration as well. So here we set up some small demonstration. So is a processor which contains like a SoC system, which contains which is an application specific computer system which used to build some specific applications. So why we need it? Because
sir,
we need better performance.
one small
Because we need better
request.
performance and
Sir, one small request. Can you share your screen,
we need
sir?
a better performance.
Hello, sir.
Oh, okay,
This is
okay.
Amarjit. I request you kindly to share your screen, sir, please.
Yeah.
Okay, thank you, sir.
Is it visible now?
Yes, sir.
So my outline of the talk is about microcontrollers, data transfer mechanisms, and the peripherals. Peripherals such as timer, interrupts, and how to use the protocols and Arduino program. So let me brief about what is an embedded system. So whether whether you are using Arduino, whether you are using 8051, embedded system is an application specific processor system. So which can build a small kind of an applications. Why we need a microcontroller based systems? So any task which is repeated after some amount of time. So the same task we are repeating. Let's say we wanted to we are doing some kind of a kind of an application like ATM or maybe some kind of a stepper motor kind of a thing, like where we wanted to do some particular task to move an object from one place to another place. So the particular task is repeated some amount of time repeatedly. So that kind of an application where we need some kind of a embedded system so that we can do efficiently whatever the task that is given to us. So what it provides? So it provides a better performance, more functions, features, and low cost and dependability. And along with that, there are some other kind of since it is a low cost, and also since it is we can develop the system within the lab environment itself, and we can deploy it. And along with some kind of communication devices are also available, so that we can communicate or we can host whatever the data that is from the microcontrollers. We can host the data so that we can share it to the other platforms also, or we can share it to the other users also. So these are the very important aspect of microcontrollers. Why we need to choose, because there are different kinds of platforms that are available in a similar kind of similar kind of environment. Another first one is the discrete logic. A discrete logic is developing that kind of a system is very tedious and also large in size, and unit cost becomes high comparatively the low cost microcontrollers. So and another one is the ASIC. ASIC means application specific integrated circuits. So everything you wanted to make a single chip. So like a kind of a like an FM chip with or maybe a armature radio. So for that you need to have a large amount of fabrication costs, and such kind of chips you have to fabricate so many, like your mobiles are having different kinds of one processor along with some memory, and again some kind of a communication devices and all. So for that you need to have a lot of costs are that are large costs are there. So the another one is programmable logic design. So for field programmable gate arrays are the previously it looks like a PLA and PAL. So programmable logic array. So means when we wanted to implement some kind of a glue function, which is like low level, which is we are trying to program the low level programming like Verilog programming. Using Verilog programming, we can prototype any kind of a our digital logic systems, like digital logics like encoders, decoders. And previously these PLD systems only is whenever it requires these microcontrollers needs extra peripherals, they are trying to use these programmable logic arrays. The next thing is that microprocessor and microprocessor along with memory and peripherals. This is a kind of a general purpose system. This is a kind of a general purpose system. In this, which is large in size and cost is comparatively high along with the microcontrollers compared to the microcontrollers. And mostly these microcontroller, microprocessor, and embedded PCs, which are software in nature. The top one are the hardware in nature. So here the architecture of the instruction set architecture of the processor remains fixed. So if you are using a 8-bit processor, the 8-bit processor architecture is fixed. So 8-bit processor contains some fixed amount of instruction set, and there will be some amount of access of your memory and some amount of access of your RAM, ROM, and some amount of peripherals. So like that, you have some kind of restriction is there for microcontrollers. But microprocessor kind of a system, you don't have any microprocessor kind of a system, you don't have any restriction, right? You can expand your memory till your processor supports. But a microcontroller based system is fixed to fixed set of architecture. So that is why I think when we heard about von Neumann architecture and Harvard architecture. In I think I have one slide. So normally these architectures are divided into categorized into two types. One is von Neumann architecture, and another one is a Harvard architecture. Von Neumann architecture, where data memory and program memory contains together, whereas Harvard architecture contains program memory, data memory separate, and the the parallelism Harvard architecture provides, because you have a separate data memory and separate program memory, whereas von Neumann architecture uses the instructions executed in a sequential fashion, because you have one set of data bus and data bus. So and also normally von Neumann architecture is a CISC kind of a processors, where your microprocessor and memory peripherals, and Harvard architecture all are RISC processors. RISC processors are nothing but reduced instruction set of computers. So in reduced instruction set of computers, so what is the strategy behind the reduced instruction set of computers is, what are the most often instructions that are used?
Sir, sorry for
kind of instruction set they will make.
Sir, sorry for interruption.
Yes.
Are you on the slide options for building embedded systems?
Sir? Huh?
Are you on the slides options for building embedded systems? I think slides are not changing.
Yeah, options of building. Yeah. Yes, I am in that slide only.
Okay, sir, then no issue, sir. Thank you, sir.
Okay. So I think the important thing about this slide is I wanted to show you what are the different platforms. What are the different platforms are there, so that one can choose the depends upon the application. One can choose these kind of platforms. So normally, I think as discussed by, as briefed by one of the professor during the presentation. So nowadays the machine learning kind of algorithms are also need to be implemented in the microcontroller platform itself. So, and the microcontroller is not so much powerful, and normally these microcontrollers are used for inference applications only. So that means testing applications only. So how to effectively use this particular microcontroller, which is constrained device, either in memory wise, either in speed wise, either in peripheral wise, it is a constraint. So a microprocessor based system is, we call it a system on board, like you see in that 8085, 8086, it's a system on board. System on board means the processor, memory is also external from programmable read-only memory, all and other devices like UART, timers, and interrupts, all these are external. But whereas in microcontroller based system, all are inbuilt, and there are only less number of peripherals only that are available. So using that, you can develop your application. And here, what are the, I think this is one of the example, bike computer. So here the function of the bike computer is to measure the speed and distance measurement. So what is the constraints here? The constraints is size, cost, power and energy, and weight. So according to that, we have to develop, according to that, we need to take this consideration into it. Then what are the inputs that are available to us? So the input is wheel rotation indicator and the mode key. And what are the output we can show? So for the user, how much speed he is moving and how much distance he covered, we wanted to show the display in that. So for that, you need a low cost microcontroller, which is a 8-bit 8-bit microcontrollers is sufficient for this kind of an application. Similarly for this, there is some kind of external peripherals that are needed to be interacted to this microcontroller. So for this, you need to have some kind of a motor controller. Motor controller IC is required to interface it, and also which is used to drive and measure the whatever the motor that is there. So here you have for this kind of an application motor control unit, you need a 32-bit and 256 kilobytes of flash memory. So depends upon the first one is a low cost bike computer, the second one is a motor control unit. So for the second one, you need a 32-bit microcontroller which requires 256 kilobytes of flash memory. Similarly, if you are going for an FPGA, let us say, so in the previous slide, so when we wanted to go for a FPGA is like whenever you wanted to have a reconfigurable system, means even you wanted to change your processor, even you wanted to change your peripherals. For that kind of a system, you need to have a reconfigurable system. So reconfigurable when you need in the hardware, then you need a programmable gate array kind of a system. Reconfigurable in software, then you need a microprocessor or microcontroller based systems. And along with that, these are, we call it as standalone systems. So, and on the top of it, if you wanted to make some a real-time operating system, you can install on this, you can port real-time operating system on these processors. Then you can make a real-time operating system based microcontroller system. So where you have a normal microcontroller does not have a timing requirement, because you have to perform this task and don't have any timing restriction. But if I wanted to perform the task within this 1 second or within the 2 seconds, like some kind of in missiles or some kind of an applications where you have a strict timing requirement is there. So such kind of systems, you need a microcontroller. Similarly, when you are using autonomous vehicles or maybe your ADAS system in your car, in that also these a real-time operating system based microcontrollers are used. And ASICs are purely, if I wanted to make one particular fabrication of one particular functionality of one application, then I will go for an ASIC. Okay, discrete logic everybody knows, so I don't wanted to spend the time again. So what are the benefits that we get? So here we will get the better performance and efficiency and less cost, all the flexibility, that is operating cost, maintenance, all these things will be reduced. So, and more features and better dependability, and also we can update the system even. And so the main functions of your embedded system is closed loop control system. It's a monitor, process, adjust an output to maintain to a desired level, or you can monitor like example speed, direction. Similarly, you can make a sequencing step through different stages of environment. Similarly, you can perform some signal processing tasks like such as filtering, removing noise and all, and then you can exchange the communication information. So these are the main tasks that are used in your embedded system. So what are the different hello? Yeah, interfacing. So finally, the outcome of this embedded system is you wanted to interact the system with some kind of a other peripherals. Then you need an environment to external environment. For that, you need to sometimes you need to take the inputs from the sensors and also from the sensors, and also some digital inputs are also you can take, and you can write your whatever the data that is that you measured from the to the LCDs or 7-segment displays and all, and you can interact with the digital switches and complex displays, and all the here in your microcontroller also all the instructions that are executed in sequential. Okay, so the microcontroller has a peripherals for concurrent embedded interfacing and control, such as analog. It can take analog signals and non-logic levels, timing, clock generation, communication, reliability, and safety. These kind of tasks that you can make concurrent. It looks like a concurrent, but it is nothing but you are scheduling in a very tight timing overlap. Okay, so this is what I think the slide is clear to you, that a processor along with the interrupt controller, so is trying to interact with the more number of peripherals through bus. So there will be a shared bus across all the peripherals will be there, so that the processor will communicate to all the peripherals. Okay, so sometimes what happen, normally usual manner, all the peripherals are interact with the processor in a time sharing fashion, because the bus that you are using is using a kind of an arbiter kind of a mechanism. But in order to avoid the, I think I have some slides that I kept for interrupt controller. In the interrupt controller, we used to see that how to effectively utilize the CPU time, so that we can allocate this processor resource to some other tasks. Okay, so CPU executes the instruction one or more thread of execution, means concurrently you are running multiple number of process, and there are some specialized peripherals are there, which are like watchdog timer, analog interfacing, timers, communication, other devices, and detecting some external events, and LCD driver. All these are is there for the these processors. And as I mentioned previously, so processors are categorized into two: CISC and RISC. So complex instruction set and reduced instruction set. So CISC contains more number of instructions, RISC contains less number of instructions. CISC is mostly Neumann architecture, RISC is Harvard architecture. So since the objective of the RISC is to perform a task within a lesser amount of clock cycles. The main aim is that. So CISC, even if you take more number of clock cycles, for even small tasks also you have a instructions are there. Okay, so here normally the processor frequency is very much high in CISC, but here RISC is mostly targeted for the low power applications. Even in RISC there is we are seeing 8-bit. Similarly, there are 16-bit, 32-bit is also there. So one of the example is ARM processor, ARM Cortex 1, Cortex 3. These are all different kinds of 32-bit microprocessor where you can perform the operations very efficiently. Okay, but of course here I am covering only the basic 8051 microcontrollers. Okay, so whether you are performing, the beauty of these microcontrollers is whatever the task that you are performing, which looks similar to whether you are doing operation on 8-bit or 32-bit, doesn't matter, because after all the processor is having a scalable in nature, means whether you are performing the same operation in 8-bit, so you are performing such kind of operations 4 times, 4 kind of more operations that you are performing in a 32-bit processor. So whenever you are performing any tasks, so the execution time of your program, you have to optimize it. So this how you will write. So time per program is nothing but instructions per program, and each instructions is having cycles per instruction, and the time into cycle, so that your here the objective is to reduce the number of reduce the overall time of your program, so that your performance will become more. So this is the, I think, Newman and Harvard. So program memory, data memory, separate data buses are there, whereas here only one data bus and one data bus is there. And this is your typical 8051 microcontroller. So now I am stick to the 8051 microcontroller. Like we will deeply study here that in 8051 microcontroller, what are the flexibilities are there, and how we can program it, and how to use this 8051 programming in a demonstrable level. So here the 8051 microcontroller, here it contains the 128 bytes of data memory, and here you have a 2 timers. Here you have IO pins are 32 and serial ports are 1, and interrupt resources are 5. So, and you have a program memory 4 kilo of ROM. So, and this 4 kilo ROM is not available to any of the other peripherals. So, whereas in your Newman architecture, this 4 kilo ROM is also available to all the peripherals. But here, it is since it is a read-only memory, you are mainly using for the program purpose only. So that is one of the things. And here, if you see, there is a oscillator. Oscillator is there with the connected to the CPU. You are here. The oscillator frequency is fine-tuned to the 12 megahertz, approximately 11.959 megahertz. But approximately we can say it is a 12 megahertz. And here it is a 8-bit microprocessor. CPU is 8-bit, which is various manufacturers are developed 8051, and you have a one interrupt controller, which is similar to your in 8085 you have a 8259. Similar kind of interrupt controller, which is inside of your chip, and you have a memory which is of 4 kilobytes of ROM, and you have a 128 bits of RAM. Along with that, there are ports are there, which are useful for connecting to the IO peripherals through using the ports. Okay, so you have each one is a 8-bit port. So 4 into 8, 32-bit ports are available to interact with the various peripherals. Similarly, here you have 2 timers and you have one UART is there. So these timers and UART will be very much useful while synchronizing your tasks between your processor and the peripheral. So that is why when we are using these kind of a communication mechanism, what are the various communications are available, so that we can use. And similar versions of 8051, why I kept the slide which contains the different kinds of microprocessor. You should know when we are choosing the microcontroller how much amount of memory that is available, so that I can develop the application. So that is also a very important aspect. Here the data memory is very limited, that is only 128 bytes only available. We can easily expand external memory, but when you are putting the external memory to bring your data from the external memory to the bus, bus to the again processor, then large amount of latency or large amount of delay will be associated. So we try to do everything within the on chip, so that what happens, our application speed becomes faster. And this is a typical architecture of your 8051. Okay, typical architecture of the 8051. So where the complete 8-bit data bus is connected with all the ports, memory, accumulator, temporary register. Along with that, there are some kind of a registers are there. As you see here in the left hand side, there is an internal RAM. Internal RAM 128. Actually, this is 256 bits. If you see 00H2, 00H2 7FH is 128 bytes. So this 128 bytes is divided into the various segments. So the first segment is which is the general purpose registers, and these registers we can use directly or indirectly. If you are using directly, means you are using the different registers. So I am not going to explain in the form of a assembly level, because here I wanted to show you we are trying to program this device using the high level programming mode. So here you have 7 registers are there, and there is no you don't have any requirement of every time we have to put the accumulator. And again, here you have a inbuilt multiplexer instruction is there, and division in multiplier instruction is there. So that will be very useful. Along with that, there is one important memory that we call it as a scratchpad memory. Bit addressable memory. So the bit addressable memory is very much useful. The memory, normally whenever you are using any memory, we are storing all the 8 bits. If you are giving address, if you are storing the data, then it asks if you wanted to store everything because the 128 bytes of memory is byte addressable. Okay, so means you have 128 bytes, each byte is having some address location. So once you are giving the address location 00, means all 8 bits are accessible to you. But if I wanted to change without using all the 7 bits, only if I wanted to change only 1 bit, so through the bit addressable memory it is possible. Why we are so much worrying about the bit addressable is, so if you are, instead of sending 8 bits and you are 7 bits are redundant and only 1 bit only you are changing, then unnecessarily you are changing unnecessarily you are using more number of clock cycles. So you can reduce the number of clock cycles using this bit addressable memory. This is a very important feature of this memory. And you have 4 register banks. So the first register bank you can use that as all the registers, and you have a different register banks that are there. Span of each one is 8 bits, and there is a bit addressable memory at 20H to 25H, and after that you have a general purpose registers. So general purpose registers R0 to R7 are there. So you can use any of the registers for doing any operation, and along with here you have a different kinds of flags are also there, but these flags will be like a sign flag, zero flag, overflow flag. These flags are available to you. So using those flags, you can use some kind of a jump instructions, and you can program your microcontroller. And along with that, here there are some special purpose peripherals are there, which are special purpose registers. We call it as TMOD register, TCON register, and TL, TH register. These are TL0, TH0 is nothing but the timer registers. TH1, TL1 is the timer registers. So I will show you in the next further slides that how to use these timer registers, so that some kind of timing delay, if I wanted to generate a particular task, how I can generate. Similarly, there is a IE and IP, IE and IP. So interrupt enable flag is also there, and also there is a SBUF. S buffer register is very serial buffer register, so which is useful for kind of a serial communication. And some more registers are there which are useful for setting the different modes, timer modes and all. And similarly here also you have a stack pointer, program counter, stack pointer. Similarly it works like a last in first out basis only here. And here there is a, yeah, I think here along with that there is a DPTR register is there. In other processors 8085 all you have a specific HL register is there, but here you have a DPTR register. So using the DPTR register you can use you can address any kind of a register as an offset to the for indirect addressing mechanisms. Okay. So this is the overview of your 8051 architecture. And when we are comparing with other microcontrollers, what are the flexibilities are there for our device, and what are the other flexibilities are there for a PIC microcontroller or AVR microcontroller? If you see 8089C51, you have 4 kilo. Different versions are available, 8K, 16K. RAM also you have 128 bytes, 256 bytes, and no EEPROM support is there. And timers, you have 2 timers. If I want 3 timers, then you have to go for a 8K device. ROM should be 8K device. 89C52 you have to go. And IO pins are 32. And the speed is up to 33 megahertz. You can go up to 33 megahertz. And the interrupts are 5. And along with the in other versions you have 6. And there is a power down mode is there, and watchdog timer. For the 8051 you don't have a watchdog timer, and voltage range is to 5 volts, and there is no inbuilt A to D converter is there, and UART. And if you see Atmega 32 AVR microcontroller only you are using in the Arduino. So you see here ROM is 32K, 64K versions are available, and RAM is 2 kilo device, and RAM is 2 kilo, 4 kilo. So the memory space is more here, and here the timers 3, 4, and speed is 16 megahertz. One of the disadvantage of this processor AVR microcontroller is speed. Okay, but inbuilt A to D converter, 10-bit A to D converter is there, and DAC is also there, so that you are getting a PWM pins. So you can program the digital IOs in the form of a PWM pins. That will be very useful for driving the loads like your loads like stepper motor or DC motor and all. So this is what here you have. You have internal RAM which is 128 bytes 002 7FH, and one more 128 bytes is there, but it is not provided to the user, which is useful for only for the internal purpose, because some of the registers address and all they are keeping in the other 7F. And there is the external RAM. It can support up to maximum of 64 kilobytes. Similarly for program memory, and in case of data memory you can maximum up to 256 bytes you can use. Okay, so this is all about the microcontrollers. And when we are programming this microcontroller, so you should know what kind of data types that we have to use. And now whatever the general C that you are using, it becomes embedded C. So here each and every operation is very costlier. Even if you write a printf statement, that printf statement itself is a very costlier. So, and you don't have a separate console or something. So you have to use your serial terminal itself as a console. And here you have a signed and unsigned, and enumerated data type, and signed and unsigned, similar to your C. And normally we are using since it is an 8-bit microcontroller, trying to use the character as in the form of an integer. So all operations are 8-bit in nature. So trying to do all the operations within the 8 bits using character only. Okay. So there is additional data types that are there, which is called bit. So these are very much useful when you wanted to use the S bit. Means I wanted to use the S bit, means that data type is using the bank 4 of your memory, because it is using the bit addressable memory. Okay. Similarly, there is some special functional register SFR and SFR 16-bit you can use. Okay, this is one simple example I wanted to show you. So where we will program all these things. So there is a Keel software that is provided, Keel. So by the ARM. So if you download the Keel software and if you write a program, maybe while we are showing the demonstration, we will show you how to program the device with a higher level programming, so that high level language programming, so that one can program the easily the board. Okay. So here I am writing the header file that is includes, which is called #include register 51.h, and I am writing a simple delay function, and here the delay is some amount of time. I just wanted to on a particular port. So here the port is P1, and after some certain amount of time, the port should be on or off, depends upon the how much time looping is done. And all these, when you are writing this high level programming, it converts into the object code, and it further converts into the assembly code, and you can see the relation between the high level programming code to the lower level programming code. So optimization can be performed at the assembly level, but when we are using high level programming, it is user friendly. Okay. So I think this is easily understandable code. And if you see here, I am just writing a for loop which contains the port I am making on or off. Okay, and calling the delay function. And now let us move the data transfer mechanisms. So because why we need is, whenever the interrupt is occurred, how the interrupt is occurring, why we need a timing, why we need timers. So how the event related operations using the timers. Okay, and what is whether we can use the DMA for some purpose. Here this microcontroller does not support the does not having a DMA capability, but some other devices like ARM and all, they have a DMA capability. Okay, so we should know the data transfer mechanisms. So the data transfer mechanisms is transferring the data from my processor to the peripheral to the processor, vice versa. Okay, so there is all these systems which are memory mapped systems or IO mapped systems. So memory mapped systems means, now this microcontroller that you are studying 8051 is completely a memory mapped system. Means whatever the instructions that you are using the same ISA architecture only, you can transfer your data to you can transfer your data to the IO, to the IO to the processor to the IO. So using the data transfer operations only, data transfer instructions only, you are transferring your data to the processor to the IO to the processor. IO mapped IO access is, you are specialized IO instructions are there. Okay, like in 8085 or 8086, you have in and out instructions kind of, but here you don't have a specialized IO instructions are there. Okay, so memory mapped IO, and each and every address of your resource is having some address. So you can access using the indirect address of that particular resource. You can call indirectly, or you can have a direct interaction. Like R0 can be call a bank 1 of first address. Okay, similarly I can directly call R1. So the second one is the indirect calling. Second one in the sense uh, bank zero bank zero address. Okay, bank zero first address is nothing but the indirect call, whereas R0 register is the direct call. Okay, so what are the schemes that are available to you? That parallel data transfer, simple data transfer, and handshaking mode data transfer. And serial data transfer, you have synchronous and asynchronous. So serial data transfer is you are sending the data in the form of a bits, and mostly both the peripherals having same clock frequency, or both the peripheral and processor are having a different clock frequency. Okay, and handshaking mode data transfer is also a asynchronous in nature. So yeah, I think this is in and out instructions. So the memory mapped IO, programmed data transfer. Yeah. So in the programmed data transfer is written and controlled by the programmer and executed by the processor. The data transfer between the processor and IO takes the executing the corresponding instructions. And directly, if I wanted to, an example of programmed IO device, IO is a byte by byte you are sending the data. Okay, so this is the one of the example. And here, while you are programming data transfer, you have two kinds of modes are there. One is polling mode, another one is interrupt driven data transfer mode. So polling mode, you are checking the status of one particular flag of your processor, and whether the data is transferred or not, you are checking. So that way you are always checking the processor status, so that process so that what happens, the processor resource is always busy. It is not useful for other devices. Whereas interrupt driven data transfer is whenever some event is occurred, that time only interrupt is enabled, then the interrupt line of the processor becomes gets accepted. After that, whatever the task you are asking the peripheral, so that will be served to the processor. So that way the interrupt driven data transfer mechanism will be solved. So mostly here the interrupt driven data transfer mechanism is very fast in nature. Okay, and polled mode is so here one more important thing here is, in polled mode also you can get the you can send the data transfer from your peripheral to the processor, but here with the delays only. Okay, so how much amount of delay is taking by your processor, that much delay you are kept in the that much delay that you kept between the data transfer, so that when the delay is completed, then the data will be served to the processor. In that way, the polled mode will be there. But what happens if multiple number of such kind of delays if we need? How we can prioritize? So those things we cannot do it in the polled mode. So that can be done only with the interrupt driven data transfer mode only. Okay. So that I will show you in the interrupt peripheral. Okay. So this is the interrupt driven data transfer, and the next one is the DMA. So in either case you are using the intervention of the processor, but without intervention of the processor, if I wanted to send the data from the peripheral to the memory to the peripheral, then we can use the direct memory access. Here also some kind of modes are there, like such as a cycle stealing or some other kinds of modes. Okay, so yeah, so this is the I am whichever is not needed, I am just skipping those things. And the next thing is serial data transfer. Serial data transfer is the you are sending the data serially to to the processor or processor to the IO. So in your 8051 you have one serial mode. So where you have a transmitter and receiver, and you are using the SBUF register which is there. So which is useful to transmit to, you have to program that in either in transmit mode or receiver mode. Okay. So normally this we call it as USART, universal synchronous asynchronous receive and transmit. Okay. So and here also you have some kind of header and payload data and CRC check will be there. So the data that you are sending in the form of a number of bits, so that we call it as a baud or maybe a symbol. Okay. So the different baud rate will be available for these peripherals. Okay. Okay. So the next thing is that the timer. So in timers you have two timers are there. So two timers are there. So both are 16-bit in nature. So whether there are different modes are there. So the timer, the basic utility of the timer I am telling you. So let's say if I am writing a for loop for generating the delay, I think in the previous program I shown here. So I am writing a for loop. That is not very efficient in nature because there is a 11.59 megahertz is there. So I am making that as as 12 megahertz and calculating all the things. So if I want accurate timing, then one should go for a timers. So what is the advantage of the timer? Here you have two TL0, TH0. Each one we call it as some 8-bit. This 8-bit we call it as lower 8-bit we call it as TL0, higher 8-bit we call it as TH0. So here you have different modes are there. So first one is the 13-bit mode. So means so the timer normally used to start with 2 power 13 is you will get some 2 power 13 value. So from that onwards, if I wanted to have a 2 power 10, so 2 power 13 to 2 power 10 it counts. So when 2 power 10 it reaches, then an overflow flag will be turned on. So that what happens, the timer finishes the job and then you can complete the delay, or you can generate the interrupt even. Okay. So that way the timer can be used as a interrupt. So this we call it as a timer interrupt. Okay. And similarly in mode 1 you have in mode 1 you have a 16-bit mode. You can directly use the THX and TLX together. So that way also you can generate the timer. 2 power 16, 65,535 minus if 2 power 10 or 2 power 6 if you say, so that you will have some value. So till that value difference that will be counted. So it counts your clock frequency. So your clock frequency is nothing but your let's say here if I am setting 12 megahertz, 1 by 12 megahertz is some amount of microsecond or microsecond. That microsecond for every clock multiplied by that many number of let's say if it is the difference is 1000 into 1000 into 1 microsecond, 1000 microseconds you can achieve like that. Okay. Similarly, the mode 2 is 8-bit mode. So normally when you wanted to use for the baud rate generator, you can use this mode 2. Okay. Similarly, mode 3 also similar. This we call it as split mode. Okay. So once TL0 is completed, then TL1 will be started, and once TH0 will be completed, then TH1 will be started. It's like a split mode kind of a mode. Okay. So here you have, it is similar to your 8085 whatever you studied. So here you have a T-mod register. This contains timer 1, timer 2, gate C by T, M1, M0. So M1, M0 will be programmed through whatever the mode that you are, whatever the mode I told. So if you are set 00, then it is 13-bit mode. If you are set that with 01, 16-bit mode, 10, 8-bit mode, and 11 split mode. So like this you can program the timers. Okay. And this is the TCON register. So in that we can find out whether whether TF flag, whether overflow flag I wanted to check here. So I can read from the TCON 7 so that the timer 1 flag will be gets coming, so that the timer 1 is finishes the job. So all these things I can here I can use this register to check the whether it is overflow flag is coming or not. Similarly, external interrupt edge flag also I can measure here, TCON 3, TCON 2, TCON 1, TCON 0. Okay. So the higher 4 bits are for internal timer flags. The lower bits are external flags. So this is what I told you, right? So 1 by 12. So why 1 by 12 is nothing but every instruction is taking 12 clock cycles. So that is why 1 by 12 into 11.59 megahertz is nothing but every instruction takes roughly operates at 921.6 megahertz. Okay. So T is equals to 1 by 921.6. 921.6 is nothing but 1.085 microseconds. So now if I am saying in hex, if I am using 16-bit mode, so FFFF minus YYXX. So this YYXX, if I remove, means whatever the time I told you, right, 1024, you convert the 1024 into the in hexadecimal. That means 7 triple F or maybe 8 triple F. So that value will become the timer, whatever the timer value that you are providing. So the TH and TL will be counted till whatever the count that is reached. Okay. So actually basically the difference between these values only it will count. Your clock frequency it will count. Once the count is finished, then the overflow flag will come into the picture. Okay. So like this, you can generate the different events of the delays, or even you can use the timer for in an event counter also. Okay. Let's say you are let's say one particular event comes, then you have to trigger. So in that case also the timer will be very much useful. Okay, this is what the counter programming, that is what here. So here the basically all the steps that are provided, we have to give the load values, and then we have to give TH and TL values, and start the timer, keep monitoring the TF flag, then stop the timer, clear the TF flag for the next round. Again you have to start the TH and TL. So if it is 2 power 13, then it is mode 1, mode 0. If it is 2 power 16, then it is mode 2. If it is 2 power 8, it is mode 3. If it is a split mode kind of a thing, then it is mode 4. Okay, so all these things are same. So all the things that are here, here I written for the one assembly code, but I will try to explain with the, I think I forgot to put the, but anyway, but even you can use the same things, same values in your C programming also. Same whatever I shown, register 51.h, and you create some variables. Okay, in that variables you can put TL0 is GRF0, TH0 is GRF00, and complement the PA port. And here this is the delay program. The delay program contains, you are setting the one, there is a TF flag and TR flag is there. So here first you have to set the these value, then you have to set the TR flag, then whether TF flag is overflowed or not. Once the overflow, then you have to clear both TR and TF. That's it. So the same thing that you can write in your C programming also. Maybe I kept some of the examples in the next further slides. I will show you. Okay, this is what your serial. Of course, the parallel transfer nowadays it is not visible, so we don't need to worry about the parallel transfer. But mostly, if you have a multiple number of lines, both sender and receiver, but in serial you have only one line, so you are sending the data at a higher frequency rate. That is the difference. Okay, at a higher frequency rate, so that you can send more amount of data. So a simplex we call it as one transmitter and one receiver. If you are considering half duplex, then both sides you have at a time only one channel that you are using, either transmitter to receiver, receiver to transmitter. So your serial communication in here in 8051 is a half duplex system. You are using mobiles. In the mobiles you are using full duplex. Okay, so that is what here in the synchronous and asynchronous. In asynchronous, we are showing usually data sent at one time is 1 byte, and here stop and stop bits are used, and gap between the data is present, and data transmission speed is low, cost is low. But synchronous, mostly synchronous are synchronous. You are multiple bytes you can send, and stop and stop bits are not, no need to use. Data transmission is fast and high. So that is synchronous and asynchronous communication schemes. So I will try to show here what are the, and here in asynchronous scheme, this is what previously we are using the, when we are inventing any send information, Morse code is used. This is also a similar kind of, but here you have a BPSK, QPSK. In communication you have a different kinds of schemes are there. So this is similar kind of that. So you are here, the 0 is represented that as a space, and there will be a mark, and when you are making the start bit, then whatever the information that is there till 7 bits or 8 bits, so that we call it as a payload. Then it will ends with a stop bit. So the overhead bits are your start bit and your stop bit. Along with that, there is a CRC is also there. Cyclic redundancy check bit is also there. Okay, so these are the some of the RS-232 pins terminologies. So they are called as protective ground and transmit data, receive data, and all. So there is some kind of a protocol that is there. So what happens when data carrier detect that is taking place during the receiver and all. So I didn't kept the, but whenever you are using this serial communication, you are using the MAX 232 IC between your processor and the your serial terminal. Okay, which is the kind of a driver IC. And this is the SCON register, serial con register. I think I shown this one here. And using the PCON register, we can change the baud rate of different baud rate of the 8051. Okay, and this way you can SMOD equal to 1. It is divided by 16, so you are getting the baud rate of 57600. Similarly, SMOD equal to 0 divided by 32, so you have, means when it is automatically updating the timer register value, some value it is generated by for SMOD equal to 0 divided by 32 gets some calculated the some value which is in between 2 power 16 to 2 power 16 to 0. So that for according to that value you are getting the this 2800H. Okay. So if you give TH1 value is -3, -6, -12, -24, your baud rate will be changed. Okay, these are standardized values. This is provided by the manufacturer. Okay, so so this is the way that you are sending the serially. If I wanted to send serial data, so to the peripheral, how we will send? First, I have to send whatever the bit that I wanted to send. If you see here, Yeah, if I wanted to send any value, first I have to set the uh, which mode that I am using, and then what is the tmod register value, whether which particular baud rate that I am using, and then I have to use the in different modes that is available in the serial communication. So if you see here, this is the transmission. In the transmission, you have a SBUF register, and along with that shift register will be there. So whatever the value, that means there is a parallel to serial conversion is going on here. So you are providing a 8-bit data that is converted serially. Once the SBUF is full, SBUF is empty, then the data is transmitted to the receiver. So then receiver buffer is completely full, then only it tries to convert that into the parallel data. Okay, like that it can complete the serial communication. So that is what here you are checking. Tmod register is you are setting the timer in the mode 2, because only 8-bit mode only you can use for generating the baud rate, and you are using the SCON register is loaded to the 50H in serial mode, which is indicating that you are using the standardized 8-bit serial mode, and then you are setting the TR flag is timer start 1. Then when TF flag becomes coming, then it is the transmission is completed. That we call it as TI flag. TI is cleared when transmission is completed. That means one character is transferred to the S buffer. So now you are now if I wanted to send the next character, again the same mechanism will be repeated. Okay, so only in the receiver side, only you have to do whether SBUF is full or not. If SBUF is full, then you can read the data. Okay, so this is the SCON register, and here this is what if you are putting SM0, SMG1 is in 0, then 8-bit shift register mode. If you wanted to use 8-bit UART mode determined by the timer 1, so you have to set SM0 and SM1 in this mode. Okay, so these are all different other modes, okay, which are not very much important to us. And finally, when it comes to the interrupt, so interrupt, here we have a interrupt is also there. So what is the interrupt? So the basic work of the processor is fetching and execution. So if any peripheral disturbs the processor's operation, means that they wanted to send the data, or maybe they wanted to receive the data for the peripheral, then that we call it as an interrupt. So a normal flow of execution is disturbed by any peripheral. Okay, so then what will happen? So I think that is what you are studying in the interrupt driven data transfer, right? So similar example is let's say if I am going on a leave to a particular place, if I am going on a leave, and then I have to give my responsibilities to one of my colleague, then I will go to visit to that place. Then once I return back, he will give all the responsibilities to me. It's like similar kind of a interrupt mechanism. Okay, here for that you have some particular flags are there. We have to check those particular flags. So as you see here, there is a whenever you are pressing any board or something, it is all default. It is there in the reset mode. So you are setting your program counter to bring one particular address. Means you are at a first go you are doing the interrupt only. So interrupt is nothing but you are going to a particular memory location, perform the task, and come back. Okay. So this is like your call and return program. Okay, and here, but apart of that, here you have a very important thing is that here there are different kinds of interrupts are there. So external interrupt is having high priority, and timer interrupt is having lesser priority than external. Similarly, similarly interrupt 1 is having lesser priority. Similarly timer interrupt 1 is having lesser priority. You have 5 interrupts. Similarly serial interrupt is having the lowest priority. So how you are connecting using these particular bits. So there are some EA bits are there. So this EA bit is tells you that whether enable which particular bit, which particular interrupt I have to enable it. Okay, and similarly interrupt enable, and also there is a one more pin. One more is there. You can check the you can give the priority also. So whether you wanted to give the timer priority, timer interrupt you wanted to give higher priority, you can give it. Okay, so that you can make that particular bit is high. Okay, so that when you are getting the timer interrupt, that will have a higher priority. Even in between the task, the timer priority comes, then it will the whatever the present execution of the interrupt will be stalled, and the timer interrupt will be served. Then later the other interrupt will be served. Okay, so this is the interrupt. So let us see some example related to the interrupt. So here 2 ports I kept. So S bit, this we call it as S bit registers. P1 square I kept P1 0. P1 XOR 0 means I use the 0th bit. P2 0th bit. Then I am using here void main. So this is similar to your timer also. You can set like this only. But the variables should be used tmod IETF, like that we have to use for timer. But here you are using, since you are using the interrupt, so tmod you are kept some value 0x21 that indicates the timer 1 mode 2, timer 1 mode 2, timer 0 mode 1. Okay, and IE flag, if I wanted to enable the timer 0 and enable the 0 and 1 interrupts, then I have to kept IE is 0x80. Then I am putting the some load value for the TH0 and TL0. I kept baud rate. Then after that what happens? Then both the timers are started. Then after that what happens? So when it is calling the timer 1, which particular timer is having the high priority interrupt, that only will be served first. Okay, so that we are putting in the in the control register, that in the IE flag. Okay, so similarly here LCD also same. Here we are using here in LCD it is a output device. So here you have 4-bit mode, 8-bit mode, and normally in LCD you have a data mode and program mode. In the program mode you are setting your LCD for whether you are using 4-bit mode or 8-bit mode, or where your control starts. Normally these are 11x2, 11x4, different kinds of things that are available. So according to that you have to program it. Okay, these are all different kinds of codes. So when you are in the programming mode, you have to give code 1. Code 1 means if you give 0x1, then it clears the display. If you give 2, then it returns home. And similarly, if you wanted to cursor shift to left, when you are moving message display and all you are doing, that time you are using the increment cursor, decrement cursor, shift right, display, shift left, all these things that you are doing. Okay, these are the different addresses of 16x2 LCD. Okay, so we are connecting the LCD 8051 LCD with 8051 using these pins. Okay, you have 2 parallel pins that are there. P10 to P107 you are connected to the D0 to D7, and PD0 you are giving the RS pin. Okay, read select pin. Another one is P21 is read write. Either you are giving a read write, read mode or write mode, and P2.2 is you are giving the enable. So to send any command to the LCD, RS is equals to 0. For data, RS, if you wanted to use the send the data, then you have to set RS is equals to 1, and you have to generate a pulse to the E pin. Okay, you have to generate the pulse, high to low pulse to the E pin to enable the internal latch of the LCD. Okay, so and the other thing that you are kept 10K port, which is used to control your display brightness. Okay, I think this is the this is there in the kind of assembly level. So I just wanted to give in the form of a C programming. Now you see RS I am kept P10, R rewrite I am kept P1 port, E enable port P12 bit I am using, and here you see three functions are there: command, display, and delay. So let's say first what is the delay program? What is the delay program? Just I am writing for I equal to 0, 7000 I plus plus. Okay, so the 7000 I calculated the if I that much amount of time is required to latch the one particular data. Okay, so after that you see after 2 times I am providing the delay, then you are going to the command mode. So when you are going to the command mode, what we have to do? First you have to generate the RS is equals to 0, RW equal to 0, and enable equal to 1. Then you have to generate a pulse. So between the two delays you are providing the E equal to 0. Okay, so you are giving E equal to 1, then delay 0, then E equal to 0. That means it is a pulse. So after that command, again you are calling the delay function, and again this command 0x38 is you are telling that first time you are putting your control at the starting point. Okay, so 3 times you are giving the same value 0x38, 0x38, 0x38. Then after that your cursor will be blinking. So to display the cursor on blinking, 0x F and 0x6, shift the cursor to the right and then clear display. After the clear display, you are putting the data in the display mode. So whatever the data that you wanted to give, let's say hello world you wanted to give. So that hello world you can send through the data display. Here I am data display. So here data display H. So here in the data display port 2, whatever the data that is there, that will come to the port 2, and RS becomes 1, and rewrite becomes 0, enable 1 becomes 1. Again in the form of a pulse we are providing, and we are giving the data like that we are providing. So in that way you are programming the LCD. So there is one more method is there using the busy flag method. So instead of using the purely on the delay, you can use the busy flag also. So I will share these slides so that you can go through it. So the next one is stepper motor interfacing. So the stepper motor, you have 2 kinds of motors. You have 3 kinds of motors are there. So one is DC motors, stepper motors, and there is another variant of motors are also there, which is having a high performance. Okay, so a stepper motor is widely used device that translates the electrical pulses into the mechanical movement. So, but normally these devices require large amount of current capability, or large amount of current capability. So that is why we are using some kind of a driver ICs. So I am not going to tell about the internal of all the stepper motor and how they are functioning and all. Here you have a rotor and stator, and here you have a different kinds of winding mechanisms are there. So at any point of time you are on the 2 opposite sides. Okay, so that you can unipolar motor, bipolar motors, different kinds of motors are there. So that when you are exciting some particular windings are get activated, so that you are getting the rotor moves. Okay, this way in the step 1 you are making winding A, winding B is on, and winding C both 0. Similarly 0 triple 1. Similarly, there is a different kinds of normal step sequence, wave step sequence, and half step sequence are there, which will be provided, which will be useful for controlling the different motors. Okay, so this way you have red, green, green 1, green 2, red, yellow, white, blue terminals are there. So maybe I think my scholar has kept some kind of a demonstration with this one. So we will show you the demonstration. Okay, this is the program for 8-step sequence and 4-step sequence. Here we written I didn't kept the C programming, but maybe this will be there in all the standardized books. But you are using one driver IC, which is ULN 2803. So that makes desirable level of your current carrying capability. That is the only thing. So similarly, 80 transducer, whenever you are using A to D converters, so can I take 2 minutes break so that I can take some water and come back?
Hello, sir.
Yeah. Can I take just a 5 minutes break?
Sure,
so
sir. Sure, sir. Very wonderful session is going on, sir. Please take your time, sir. Please.
Can you have some water?
So till now, sir has explained all the concept very clearly, starting from the architecture of microcontroller, then comparison in between CISC and RISC, followed by interfacing, and now he is showing all the programmings, not only the basic programmings but also the interfacing, stepper motor. Now he is going to show the ADC interfacing. So this is very fruitful for the students at all levels, because all of we now doing programming in microcontroller, but the interfacing is the most important thing. So if you can indulge and involve this program, then you can get the idea more clearly. Please stay tuned. Sir will come back within 2 to 3 minutes.
You sent everything. Just 1 minute. Because I prepared so many. Okay, let us continue the ADC. So analog
Welcome,
digital
sir.
to ADC is having single channel or multi-channel ADCs are there. So here ADC 804. In our board we have a 809, 804, 809 is a similar kind of variants. The difference between the 804 and 809 is a single channel and multi-channel. Okay, so why we need ADCs here? See, now you see the processor at one frequency, the peripherals are at different frequencies. So in order to communicate both these two, now what we studied is, one is interrupt we studied, another one is timer we studied. So using these two to make sure that any peripheral, let's say one sensor is connected to the ADC, ADC is connected to the processor. But the your sensor is working at different frequency, very low frequency. And your processor is at 33 mega, like maximum is 33 megahertz or 11, 12 megahertz. So this is at very high frequency and that is at very low frequency. How you have to synchronize both? So using either polling method, either these delays, using the timers, or either interrupt. See, all these three mechanisms that you can use in between any kind of peripheral. So you think that
Sir, you are not audible, sir.
you have parallel ADC, you have D0 to D7 is available, then you can take all parallelly together. But what is here the important thing is that V in plus and V in minus and V reference byte and analog ground and digital ground. So, and a clock in, read and write, and a chip select. So these are the very important pins. Okay. Sometimes what happen, your see this ADC is either 8-bit or 10-bit or depends upon some number of bits that is there, right? So according to that, you are having the resolution. So if more resolution is there, more amount of speed will be there. Okay. So means lesser number of bits having more quantization error, but they are very fast. Okay. And if you see, you have here this 804 ADC is, you have 5 volts and resolution is 8. So means you can represent your analog values between 0 to 255. Okay. So means all 0 to 5 volts is mapped into the 0 to 255. Okay. So, and one more important thing is the conversion time. Conversion time is that conversion time is defined as the time it takes the ADC to convert the analog input into the digital output. Okay. So here the 804 conversion time depends upon your differential clock signals. So, but it cannot be faster than 110 microseconds. And finally, your clock frequency depends upon 1.1 by 1.1 RC. When you are taking the typical values of capacitor and this one, you are getting a frequency of 606 kilohertz. So your conversion time frequency is almost 606 kilohertz. Okay. So it depends upon the different step sizes. So if I am using the complete 256 levels, so for 1 bit to 1 bit you need 3.90 volts. If I wanted to use 2 by 256 levels, if I wanted to use the V reference is 1.28, 1.1, 2. So then your step size value will be increased. Okay. So you have a lesser number of step sizes. Okay. So the remaining thing is that whenever whatever the analog signal that you are providing, you have to use analog via analog ground, and digital signal that you are using digital ground. And chip select is making whether it is if you are using the chip select equal to 1, then it will be if it is 0, it will be activated, otherwise it is not activated. Similarly, when output enable is, because these bits are in the form of using these bits that are using a tri-state buffer. So when your output enable is 1, then only your output you are getting from the D0 to D7. So write signal is indicating the start of conversion. So INTR indicates the end of conversion. So how the conversion will be taking place? So the moment when you are sampling your analog signal, then you are pressing the start of conversion. Then you are waiting for some time till the whatever the conversion time that is there. That means you have to use some kind of a delay. Then a signal, an output signal that will be generated, which is called entra. So till that point, you have to wait. Okay. So that once the conversion is taking place, that is the equivalent digital value of the particular signal. Okay. So D out, digital out value is nothing but your Vn by step size. So using the formula, using this particular formula, so one can use the how much amount of step size is required, how much amount of equivalent digital Vn is required, and all. We can use it. Okay, we can develop it. And this is what here, as a chip select becomes low, it gets activated. Then write bar equal to 1. D0 to D7 data is coming at the after conversion. So start of conversion will be your RD bar becomes your write bar becomes 0. Then that time your INTR is low. When your end of conversion INTR becomes low, means your conversion is completed. That means at this point of time you are getting the data out. So when your read is available, when your data is available. So that's why the RD bar becomes 1 till the data out is available. Okay. So through programmatically you have to write this programmatically, or using the timers, you have to find out how much time that is required, right? And this is also asynchronous with the processor. That is the one of the major challenge. Okay. So interfacing the ADC 804. So here you see here the same thing that whatever the things that are there. So I try to explain with the so here previously I am taking only single channel output. Here I try to take multiple channels. So multiple channels means 809. In 809 you have 8 channels are there. So A, B, C are the different channels. So for every channel you are taking some data, means maybe you think that there will be a mode. That mode contains pressure, temperature, and some other physical quantity. Okay, rotation. So all these three you wanted to take from the different channels, from the different sensors, and you wanted to send to your processor. Okay, and you wanted to send to the processor, and processor do some calculation and provides your display. Okay, so whatever the example that I provided here, write bar, INTR, read bar, same action is there in your code also. Okay, so ADC conversion and end of conversion, start of conversion, all these things are the similarity. So similarly DAC is opposite to that of your ADC. So when we wanted to use the this one is useful for generating the different waveforms, like sawtooth waveform, like triangular waveform, different waveforms that we can develop using. And also one more important thing is that PWM pulses also we can generate. Okay, so this way you can generate some kind of DAC. So normally I think when we are studying the in microcontroller basic subject, so R2R ladder approach is there. So using the R2R equivalent ladder approach, one can use the one can develop the one can convert the analog signal into the equivalent digital signal. Okay, digital analog equivalent signal to the digital equivalent signal. Okay, here there is a 8-level ladder is there. Okay, so resolution, accuracy, and full scale output voltage is the, so there will be some if you are going to a bigger bit ADC, so your accuracy will become, okay, since your resolution is more. Okay, so this is the one of the example how to generate a staircase waveform. Okay, so similar small programs only. So I am leaving to you that task to you. So because the one more important topic is there, so that I can finish it off. So this is serial communication, how the bits are processing. Since now we are covering the protocols. So why we are going for a protocols is, so whatever the sensors that they are sending the data, they are having a certain sampling frequency. Okay, what happens if I wanted to have a higher amount of speed of my processing? So that time, what kind of how can I handle? Or if I am having a multiple number of sensors, how can I arbitrate the different number of sensors? So for that, you need some kind of an intelligent protocol system. So serial communication is like you are sending the data serially from one peripheral to other peripheral, and at a time one transmitter can talk to the other receiver. Okay, so this is like your shift register. Okay, so you have this is like a shift register. Okay, so a simple serial link. So now we will come to one juncture that we call it as SPI, serial peripheral interface. Okay, so here you have two shift registers that are there between the master and slave. So anything communication happens between the master and slave. So master is always the initiator, slave is always the receiver. So the master sends the communication to the slave, okay, in serial fashion, all the bits. Okay, so here also there is shift register is there, here also there is a shift register is there. So there is two kinds of inputs are there, SDI, SDO, SDI, okay, which are connecting to the same clock, okay. So this simple serial link, they are connecting to the multiple number of slaves. So these slaves, assume these slaves are connected with a different number of sensors. So I can arbitrate different number of sensors using and even I can have one particular address to the one particular, not here there is no address is available. Here there will be some kind of decoding kind of a thing will be there, which is of your SS bar. Based upon the SS bar, we can identify which particular peripheral that we are selecting. Okay, so this we call it as a microwire operation. This is developed by Maxim, I think, Motorola. It is developed by the Maxim Motorola semiconductors. Okay, so here there are multiple peripherals are there, standard clock, different number of SDI, SDO will be there. Okay, and here you are connecting all the ports. SS bar will be connected to the standard decoder. Okay, so but here the problem with here is in the simple link. Here in the SPI, which particular slave is get activated, which particular slave is sending the data. Okay, and if there is a error is in between, if there is some kind of error bits are there, if there is in this communication, if there is some kind of error is occurred, then how to debug it? That is one of the challenge here. But it is very fast in nature. Okay, mostly whatever the peripherals that you are using, like whatever the peripherals that you are using, like camera, so these are all SPI based. Okay, and the next one more kind of a interface is I square C. Okay, so I square C is inter-integrated circuit bus. So where you are having a sensor nowadays, what happens? The sensors are coming up with a I2C interface. So you have a sensor. Sensor is already connected to the I2C interface, and you are getting the I2C interface output, not the sensor output, because they are clubbing in one sensor only multiple number of parameters. So let us say if I am taking the one humidity sensor, humidity you will get, temperature also you will get, some other thing also you will get. So multiple number of parameters you will get from a single sensor. So for that you need a large amount of data rate. So for that you need a special purpose protocol. So which is based upon the pull-up resistors. Okay. So I think from the VLSI point of view, like you have a PMOS and NMOS. When PMOS gets activated, when you are giving the when your logic is 0 at the input. So right, so that we call it as a PMOS. NMOS, when transistor becomes on, when NMOS when the input is 1. Okay, so the name it is also having a master and slave relationship. But here what happens, multiple number of peripherals are connected with the pull-up resistors. So then what happens, any peripheral, if I wanted to send the data, it will pull up. So that what happens, you can identify that peripheral, which particular peripheral that is sending the data. Okay, through SCL and SDA you can send your data. Okay, so using any node can only pull down by SCL or SDA line at logic 0. It cannot force to a logic 1. So this plays important role in the I2C. And there is for every peripheral you have a different address is there. So because of these overhead bits, this particular provides more amount of security. Okay, previous one is not having any security. If there is a debugging also, it is difficult, but here you can debug it and also you can provide the security also, because address. Okay, and you can identify where is the communication is happened. And here when you are sending the data in SCL and SDA, always you are sending in the form of a low to high, high to low. So if you see, you are having a start address, you have a SCL and SDA pins, and when you have a the byte following the start condition is made by the 7 address bits and the one direction bit, read or write. So for every data transfer you will get a one acknowledgement bit. Previously, whether the data is sent or not, you don't have any acknowledgement bit, but here you can have the acknowledgement bit, and whether you can read or write. And once the data transfer is completed, then you are getting the stop bit. Okay, but whereas the previous one, how many number of data bytes that you wanted to send in a juncture depends upon, that means the data rate is depends upon the peripheral, whereas here the fixed number of data bytes in SPI. Okay, that is the difference. And when the communication is happened, when SCL, so how the communication will be happen? So a data transfer is started by the master signaling the start condition, followed by the 1 or 2 bytes containing the address information. Then start condition is defined by the high to low transition from high to low transition of SDA when SCL is high. Okay, when SCL high and there is a low high to low transition is there. Okay, similarly stop condition is also similar, low to high. Okay, so that is the protocols. So the implementation of protocols, I didn't kept any programming part here in this base, but I hope this information is sufficient to get some kind of familiarity so that you can start. So I just quickly go through the Arduino also so that you can see. I given the handover to my scholar so that he will show you the demonstration, and in the meantime, if you have any kind of questions, you can ask that time. So Arduino is some kind of a it's a AVR microcontroller. You are and it is very cheapest device, and you can prototype any kind of a thing in the lab environment itself, and you can connect using the some USB cable directly to the Arduino like the PC. Similarly, here also in your 8051 also you are doing the same. Okay. Only the thing is that it is very cheap, and can be programmed, and it can be reconfigured at the different environments also. Okay. And yeah, so Arduino is an open source platform with input and output pins and analog and PWM pins, and price is about $20 only. Okay. So this is the Arduino software, and this is the upload code for the Arduino board, and compile and check. And here you have a program setup and loop. In between that only you have to write your code. And here mostly you are using the libraries. Okay, mostly you are using the libraries of some already existing kind of a, let's say if I wanted to use the temperature sensor, already temperature sensor library will be there, so directly I am using it. Okay, so it is mostly like a development platform. It is not like if you wanted to have a commercial, if you wanted to make a commercial prototype within a less amount of time, then you can do in the Arduino kind of a thing. It's like a proof of concept. So the program you have to write within void setup and void loop, and for here you have a here there is some kind of a spec is there. So you have to write if your output port is connected to the one particular pin, you can write pin mode 13 output, and if you are writing that particular pin output means you are connecting some LED and all, then you can do. And similarly there is a delay function is directly available here. Delay 1000 means delay 1000 seconds, or delay 1000 yeah, so delay 1000 means you will get a 1 second delay. Okay, so like this, see, whatever the task that you are performing in 8051, they are available like a function to you now here. So you can directly use it and develop it. But why you are studying 8051 and other things are how to, these are if I wanted to optimize according to my application, then there you can do it. But here it is not possible because they are not provided to modify the digital right. Okay, this is library directly available to you. You have to make use of to develop the application. Similarly, if I wanted to use a serial terminal, I can use some kind of a JTAG port will be there. Directly you can connect here, so that serial console will directly coming into here. Okay, so in this slide that is what I shown here. Okay, and this is the serial monitor. So if I write serial begin 9600, if you set the baud rate, then if I am giving random 100, so you are getting a values between 1 to 100 randomly. Similarly, you can print any kind of message and all. Serial print. You are using serial console as a debugging purpose. Okay. Similarly, if I wanted to, write some kind of turn on LED with some amount of delay, that also you can do. Okay. And similarly, if I wanted to do some kind of a serial monitor, I can do. Like if I wanted to, if I perform some kind of an operation, how can I print out? Similarly, if I wanted to do the looping, so how that can be looks like. So serial print sum by 100, sum by like sum of the 100 values. And you can print all the things in the, like, since previously you are using printf, here you are writing serial printf. Okay, serial terminal that you are using as a printf. And there is one more important function that we call it as, since this particular device is having inbuilt ADC, so an inbuilt 10-bit ADC is available. So that means you can take a 10-bit so that you can take analog value, you convert into the 10-bit equivalent value. Okay, and you can analog pins are more. Okay, but the value in between 2 power 10 means you have 2 power 0 to 1023. Okay, so but only thing is that you have to find out the correct equivalent value, because some kind of scaling that you have to incorporate so that you will get the correct value of the analog of the digital equivalent value. Okay, the scaling I will show you in the next couple of slides. So let us say here, you see here, this is the some kind of ADC. So here I am taking the ADC value and analog read temperature pin. So the temperature pin, if I multiply with the scaling between the voltages are between ADC value is 0 to 5, so multiplied by 5 by 1023, so that and there is a formula for a degree C conversion, 100 into voltage minus 50, so you will get the value in the form of a degrees. So this is the formula that is provided by the manufacturer. Okay, so only this scaling is very important. Okay, while using this Arduino kind of environment. And here similarly, if you are using a light sensor, instead of temperature you are getting some light. Okay, okay, so similarly you can use the light sensors also. Okay, so one more thing I wanted to tell you is, when we are using this one, you have to use the I wanted to host my data, I wanted to do some kind of data analytic operation. So what is the temperature trend, what is the pressure trend, so I wanted to put this data onto the cloud. So for that you are using a ThinkSpeak. It's a free web service which can store all the data into the that you are doing from the whatever the data that you are collecting from the embedded system, that you are putting onto the some kind of a IoT, some kind of cloud platform. Okay, this is the environment. Just go to the website of ThinkSpeak and you can check. And there are so many people are hosting their data onto the public cloud. This is a public cloud, and you can see temperature, like different temperatures, office temperature, office like different physical quantities. You can host it here using the ThinkSpeak. So here what I do is, so I am using whatever the temperature sensor that we are using previously, that temperature sensor I wanted to put it on the cloud. So how I will do it? So that is what the task. So this is the formula that is provided by the that TMP360 is one kind of a temperature sensor. So using the in order to make the linear scale, so you will get the y equal to 100x minus 50. Okay, just go through these slides. So here my formula will be y equal to 100x minus 50. So whatever the x that I am getting from the equivalent analog voltage, I multiplied by 100 minus 50 if I do, then I will get the Celsius. Okay, degree in Celsius. So that only I am using. And here when you are using this kind of a device, your controller should have some kind of a Wi-Fi device. Okay, because until unless if you don't have a Wi-Fi device, how that can be communicated? Correct. So you need to be connected with the Node MCU, or maybe a Wi-Fi controller is required. So for every network you have a SSD ID and SSD secret password, and these are the things that you have to provide. And this is a standard template for the connecting the connecting the some kind of sensor to the cloud. So using this template, we can make our physical we can make our temperature sensor data to connect to the cloud. So this is the complete program. I am explaining step by step for each and everything, and after that you are getting the channel value is like this, and finally the temperature at different times your temperature data is showing like this, so that you can perform. Maybe the next part is that maybe you can use some kind of a machine learning kind of a thing also you can do. Okay, nowadays embedded machine learning is one of the hottest area in the for developing the very energy efficient applications. Okay, and this is the thing. So here you have a SSID and SSD pass and a secret channel ID and API key. This you are getting from the, once you are logging into the public cloud, then you will get, they will give some key, and you have to put that key, so that what happens, your device is in synchronous with the cloud. Okay, so then what happens, you are using some kind of a libraries that are related to your ThinkSpeak.h, Wi-Fi driver Wi-Fi driver, that Wi-Fi 9.h and secrets.h, and then you are using the serial communication, and then connect Wi-Fi and read temperature, then ThinkSpeak write. These three actions that you are doing. So connect Wi-Fi, what you are doing, read temperature, you are reading the temperature from the sensor, and that sensor value you are putting onto the cloud. Okay, and again if you wanted to sample and one more time, then you are using the delay. Okay, so like this you are doing, you are hosting some value into the cloud. Okay, so these are all completely standardized. Only here only our main part will be there. Where is that? This. Okay, the remaining things like this one, writing part, and that other part is remains same only. Okay, so this is what. So the references are from the reference slides are from Hans Peter Halverson Arduino programming, and MK Patel 8051 controller systems. From that I prepared all the slides. Okay, I think everyone please be there here, so that my scholar will show you the demonstration in both the platforms, in Arduino as well as the microcontroller, both the platforms he will show you the demonstration. So I'm making the video on. I think you can see here. This is the Arduino device. So I have to make on. Just you make it bigger. Is it visible?
Yes, sir.
Is it visible? Is visible? So similarly here, I just wanted to show you the how I can show here. Show me here this one. Yeah. So this is the 8051 microcontroller board, where here there are all the peripherals. Everything is within the board itself. Where if you see ULN IC and 8051 LCD, all are connected in a single board. Okay, so that you don't need discretely, you don't need to do in the you don't need to do it. Okay, so that is why we are using for lab experimentation purpose. Our students are using this one. Similarly, in Arduino interface also he will show you. So we are connected all the different kinds of experiments in one particular place. So one experiment he will show you. Okay. So I hope definitely that will be whatever we discussed. He will show you the program. He will show you the demonstration so that it will be more clearer to you. Okay.
Yeah. Thank you, sir, for your presentation.
I think.
Yeah, sir, can you please go to your first slide, please, because we have to capture one image. Your first slide, sir. Okay, thank you, sir.
So I think he will log in into the mobile, and through mobile he will show you the. I will forward that link to you. So you just log in through mobile. So I think during pandemic time, I think our students are using these cloud environment only. We make use of the programming all the students in this way only. There is one more environment is there where we are using ARM programming, ARM embed. Okay, so that is a more like it is similar to your Arduino only, but much more flexibility is there from the like either you can do machine learning or either you can do some kind of IoT. All these things are available in a single platform. Okay, so I think go to the ARM embed website so that you will get a lot of ideas there. And now I think my student will show you the demonstration so that sorry. Hello? Huh?
sir.
Hello, good evening all.
Yeah, good evening. Please proceed,
I'm
sir.
Debras Rangababu, sir. It's my screen is visible, sir.
Yes, yes.
So-
Please go ahead.
Yeah. Before doing this simulation, I'm suppose you want to do it on the hardware, actual hardware. So I'll tell you one software emulsion online available freely where you can play. The students can play with those things. So just you need to go to site called Tinkercad, where we can design the circuit can be designed and we can write the program and simulate it there. So whatever sir has discussed about the program, all thing you can simulate here on the Tinkercad. Just a second, I can. So if you get into the Tinkercad website, then you can log in as an educator or as a student. After that, after logging through your email ID, you will get this kind of scenario. Now, what you can have to do, you can click here and you can go for a new design. So in the new design, it will ask it is a 3D design or circuit design. We are doing the circuit, so we can click the circuit design. So after that, one platform will be available as to design our circuit. So in the circuit, we will have a component, or you can say the breadboard, where we can bare board it is, where you can fit all the components and connect it to the hardware or the any board, and we can play with that. So to get this board, we can write it here as, here the components are there, basic components, so let us make it as all. So we'll write it as breadboard. So one breadboard will be available. So when you write this breadboard, so different breadboards will be available here. Select this one, then you can put it here. So one breadboard is appear in front of this us. Now what we'll do, breadboard is available. Now we'll go for a Arduino board. So we'll write here Arduino. Then we can write here the Arduino board. So you can place the Arduino board. And suppose simple example we'll do just to glow an LED with the program. So we will need an LED here. So simply LED. Let us take a red LED here. Okay. After that, we can go for a register. We can connect. Let us take this. To do the connection, what do you need to do? Simply when you place on any of the holes or any of the pins, automatically wiring terminal will be appear here. We can connect those things as a wire. Now I place this. Suppose I place this here. Now I can see when you place this LED, it will show the cathode and anode. So this is our anode. So what we will do? Suppose our program here is we want to turn on the LED after certain kind of delay, turn on, turn off like this. So what we'll do, we place the LED, just we place it here. To connect the LED, this is my anode. So I will use, because Arduino board has different pins, these are the digital pins, these are the analog pins. we want to send some digital signal here. So what we'll use, any of the pin can use it here. So let us use the pin number 7. So I click it here. So again click, again click, and I place it here. So this is now connected. Now this is my anode. This is my anode. So I put a resistor in between this. So you can change the. It can be horizontal like this. So I place it here. So as you know, breadboard it is vertically connected. So already it is connected. Now let me place this LED here. So this side also connected. Now double click this. You can set the resistance. That it will be 1 kilo ohm. Is okay. After that, connect this cathode to ground. So our ground is available in Arduino board. This is ground. So now my Arduino board is connected to the LED. Now we'll go to write the program. So to write the program, the physical part is open. The coding part is just click on the code. So we'll click on the code. You will have block coding is there. So better we'll go for text coding. So text coding, what you have seen. So as the moment I click it here, by default, it is showing the program here. So in programming of this Arduino, as sir discussed, we'll have the structure says that we have two sections. One is void loop section, another one is void setup, another one is void loop. So in void setup, we are initializing the board. We need to set if which pin we are using. The pin are using as input or output like this. After that, we can go for void loop section that it's running continuously. The void loop part is running continuously in a loop fashion. So you can see the transition of your input, output, all these things. So first of all, we have used the pin 7. So in pin mode, we mention the pin 7 here, and that pin is used as my output pin. So in the void setup, I am telling this to the controller that because this program I need to flash it on the controller. So I am telling that pin number 7 I am using as the output. Now in void loop part, I am saying digital write because these are the different function: digital read, digital write, analog read, analog write. Because I want to send a digital data to that pin, so I am mentioning digital write. Which pin? Pin number 7. I am mentioning pin number 7 here as high. So it will, the LED will glow. After that, after certain delay 1000 means generally delay function take in milliseconds. So if I'll mention 1 mean this 1 millisecond, here mention 1000 means it will wait for the 1 second. Now after that I mentioned digital write and the same pin number 7 I'll make it low. So it is high, low, this pattern will go on. So with this the program is finished here. Now I will start simulation. Then you can see the LED is glowing here. Just a second. So you can see accordingly the LED is glowing. I mentioned is a high, low, high, low. So accordingly it is glowing. So it is up to you. Whatever you can use different sensor also based on the sensor data. You can get the output. So here I have designed one thing. Let me show you. This I'm stop simulation. So I show you how to connect these, how to pick up element, connect all these things. So one I have a small one. Okay. Suppose I just use what one. This is what automatic night lamp. So what it is doing, I have I have taken one LDR sensor. LDR sensor is light dependent registers. So based upon the light fall upon it, the resistance value will be changed. Accordingly, the output voltage will reflect on the output. So we have to see that it is one LDR has been connected. So you can get the connection like this. Two terminals are there. So as I am using one sensor here, so the sensor will sense the light and give the electrical output voltage to the Arduino. So I will read via one analog pin. So that's why this sensor one this sensor one pin is connected to this analog pin A0, and another pin is connected to the ground. So through this pin I will read whatever voltage I am getting depending upon the light fall upon it. And similar way I have connected one light. So same way this through register I have connected through pin number 9. And this is what. So my concept is what, whenever light fall upon it, I can control the light because it's a simulation. So I can control over here, but in real time, you have to put this on the sunlight or in the outside so that light is falling upon it. When it becomes dark, automatically this light will be on. So what I need to do, let's go. And another one is I have connected one LCD here, and LCD also start shown in the PPT that what are the different. So LCD having different control signal like enable, RS and RW, and the power supply and ground, and 8 number of data ports are there, where I am using 4 line here. So if you look into the program over here, so here what you have done, for to this operate this LCD directly, you can include the liquid crystal hex the header file. It's available on the Arduino library, so no need to write the program, specific program for this. Simply we can use their function. So what I mentioned here, so RS, it's a RS12 EN11. So what I have done, pin RS of this LED LCD is connected to 12 number pin on the Arduino board. You can see over here register select RS is connected to this 12 number pin. Then enable 11, and the 4 data pins I have used 5, 4, 3, 2. Here these are the 4 data pins. Now sensor pin I have mentioned equal to A0, LED pin I have mentioned 9, sensor value I am initialized to 0. So in what setup part, serial dot begin. So if you want to get the value on the serial monitor, so we need to initialize the serial monitor with the baud rate 9600. Why we are using the serial monitor? Because light falling upon the LDR and giving certain random value. We don't know that with how much light, which value we are getting. So what we'll do, we can change the light, and according to our requirement, suppose some less intensity light is there, and at that moment whatever value we are getting, we can take that as our trigger value. So that's why we are using the serial monitor to continuously read what the value we are getting from the light LDR sensor. So I begin this LCD begin. Now this 16x2 LCDs will start. LCD begin by default, this is a command available under this header file. So directly it will initialize the this LCD pin. Now LCD clear, first initialize, then it will clear this content of the LCD. Now initially it will print LCD print welcome Arduino. After that we have selected LED pin output because we have connected one LED is there. Then inside loop, first what we have done, we gave some delay. After that we clear the LCD, then we set the cursor, because this is a function from the liquid crystal dot header file. Set the cursor means this LCD having 2 lines. So we have mentioned 0, 1 means set the cursor to column 0 and line 1. So it will start, it will show the data, the whatever message we want to show on the display. It will begin from the second line, because we have mentioned 1, line 0, line 1. Okay, but it will clean on the line light 1, good morning. After that through analog read from the sensor pin we have connected, it will get the value, sensor value. Then we'll print the value on the serial monitor. After that, according to our requirement, we'll check what the sensor value we are getting. Suppose I have mentioned If the sensor value is less than 900, means if the light intensity is less than 900, what it will do, the LCD will clear first, because earlier LCD is showing good morning. Now it will show what? It will clear the LCD output, then the cursor will set to 00, first point. Then LCD print low light, because we have mentioned in the loop, in a conditional statement, that if sensor value is less than 900, so obviously it is now dark, so low light is there. Now we'll set the cursor to the next line, and it will say switched on the ball. And in digital, right, we are switching on the ball, because we are mentioning LED happiness high. And otherwise, the LCD will again clear, and so the highlight and the digital right will be low, and show the switch of the ball. So what we have put the logic here, when light is intensity is less, so on the display it will show low light and switch on the bulb, and the LED will glow. When the light will be high, or otherwise it will show the light is high, LCD show light is high, and switch off the light. No need to switch on the light, and this light will be off during that time. So this is my code I am running, start simulation. So now the code is running. Now let us see the serial monitor is available here. I'm opening here. Now it is, so if you click here, it is showing, a controller is showing here. Now see, I put towards the light. Towards light, it is dark. So suppose this much light is there. So how much I am receiving? 966. In the time, what it is showing? It is saying that highlight. Highlights with LEDs off. See, the light is off here. So I have mentioned the trigger value is 900. So let me reduce little bit. You can see the receiving value is 960. Again, light is off. When I put it there, receiving value is 951. So let's go below 900. So now still this is 925. So still highlight and switch off the bulb. Now I will go below, then see it is low light, switch on the bulb, and the LED will be glow here. Earlier it is a white LED I have used, that's why it is showing like that. As the time it will be below 900, it will be showing on the switch of the switch on the bulb, low light, and the light will glow here accordingly. So in this way it will work. So you can mention, you can put any sensor, and through serial monitor read the sensor data as per your requirement. Wherever you want to set, accordingly you put the conditional statement that if sensor data is this much, do this or do that accordingly. Suppose you doing a robotics one, and what will have in the generally robotics, what you are using, wheels are there, and we'll put a sensor about the wheels. So what will happen if suppose obstacle is coming in front of the robot, or this the motor vehicle what you are using at the robot. So we have the sensor will sense the distance. If the object is come closer to this, sensor will trigger that. Now the object is very close to here. You can control the motors. Now the motor will be off, and the robot will stop moving. So one setup I have make it here in the here. Let me show you. Not here, in the hardware I have made it. So this is this is the setup. So here I have mentioned it is the wheel connected. This is the motor what I have connected to the Arduino. LCD has been connected, and this is what ultrasonic sensor is available here. This one. So what it is happening? So when I connect the power supply. Just a second.
Practical implementation is going on.
So here, if you are able to see, this wheel is moving in one direction, because this is our sensor. In the sensor, suppose in front of the sensor nothing is there. Now nothing is there in front of the sensor. So what we'll do, we'll intentionally put an obstacle in front of the sensor. So let me put my hand here. So it is moving in one direction and see LED is also off. LED off means the motor is moving.
Sir, you are not audible.
Okay. Sir, mic is on. Hello? Sir, audible? So if we put the hand into this, the light will off, then only this one, and the motor will start, and it will not start giving also. The motion now is basically the restriction. So if you very ladies, it is moving forward. The motor is getting jammed there. So I think the sensor control the robotic device. The downline guiding what is being done. So this is how it is working. So that's all from my side. You show the 0.5 the most for is still there. Hello? Sir, am I audible?
Yes, yes. Please proceed, sir.
So that is how we can use this Arduino board. And if you go for the 8051, sir, so this is about Arduino board. We can play with this. Now, in case
Okay.
of this 8051, will run with another software. So, shall we go for this 8051?
Okay, so I think we have Sarah's described very in depth the 8051 and the interface programming, and whatever you have also shown, sir, using this Arduino programming is also a valuable one. So we may conclude now if Dr. P. Rangababu sir permits. So may you please hand over this mic to P. Rangababu sir?
I think I thank to your authorities for providing the opportunity to Thank
Sir,
Yeah, I'm very much thankful to you for providing the opportunity. So we will conclude here.
sir, you are not audible. Can you be little bit louder, sir, from your side?
Yeah.
Yeah.
So
sir.
is it audible now?
Yes, sir. Yes, sir. Yes, sir. Fully audible, sir.
So
ca-
I am very much thankful to all the participants and also the organizing committee of this particular talk. And thank you one and all.
Sir, actually, sir, we are very thankful. Can you, sir, please switch on your video, sir? Yes, sir. Yeah, sir, it was a very nice experience. Actually, you have started from the very beginning the architecture and how can we use in terms of peripherals its basic programming you have also shown, which is very important, and followed by this Arduino programming, and very frankly saying this was beyond our expectations, sir. So thank you, sir. And if from our student side, if there is any query, you can feel free to ask, sir. Anyone, any type of query? Students, please. Okay, so even if you have any query, you can drop to me and I may contact in after some days to sir. So thank you very much, sir, for your wonderful talk. Have a nice day.
Yeah,
thank you, sir.
Thank you. Thank you.
Yeah. Yeah. Okay, so dear participants and sir, tomorrow the session is from 4 to 6, and tomorrow there will also be a PR presentation using this microcontroller and its practical implementation. Thanks all of you for joining today's session.